Hello everyone, I'm Tejas Anvekar and I'll be presenting the Perceptual Observatory Characterizing Robustness and Grounding in Multimodal Language Models. With increasing multimodal language model every day, recent benchmarks fail to assess the true perceptual capabilities of these multimodal language model, but rather only assess the end task accuracies like VQA, etc. We also observe that these models scale only on the language side, but the vision side is frozen and unchanged. To assess this, we start creating a benchmark of both in distribution and out of distribution sample, where in distribution is just pixel level augmentations and out of distribution are structure preserving with stylized changing illusions. These are few examples of augmentations of what a single image can have. And to generate illusions, we use diffusion plus QR control net to have a canvas or a desired image along with the style to get a illusion image. These are few examples of out of distribution samples. The main motivation is just looking at this image, it looks like sand dunes. But now introducing the reference image, humans can clearly perceive what's the difference. Similarly, it is hard to identify what is hidden in these mountains, but as we have the reference, it is easy to understand what text was hidden and where. Now, we assess multimodal language model for a similar task. First is a simple image matching where you have a support image and four options. The right option is either out of distribution image or a in distribution image like Gaussian blur, and this is done for all the tasks. Humans perceive images on abstract shapes, so they tend to answer right, comparing to multimodal language model which only perceive image on semantics. We try to make this task a little harder by first making a grid or a collage of this image, and now it's a grid pointing game. Human perception is invariant to grid location even when shuffling, but multimodal language models are susceptible to grid change locations. Finally, we do attribute localization task, which is divided into two sets, full guidance and partial guidance, where full guidance you get all the attributes and partial guidance you only get one of the attribute and you're asked to perform attribution on the query image for all the attributes. Human perception is robust to out of distribution samples, whereas multimodal language models are very susceptible to such changes. Finally, consolidating all results across all tasks and both the datasets, we see that out of distribution samples hurt even larger models like Qwen72B and Gemma27B. Robustness doesn't really guarantee with increasing the model parameters. Example, Gemma12B is much brittle than Gemma4B. Scaling on the language side doesn't fix the issues, as all the red highlights you see are the delta between smaller model and the larger models. Finally, having a reasoning chains, that is thinking mode on for intern VL, you can see that all red highlights showing that the thinking versions are much worse or brittle compared to their baseline counterpart. On the other hand, humans do almost perfect job, having more than 95% accuracy across all tasks. To get deeper insights, we provide multi-dimensional insight. For example, in task 2, which is grid pointing game, we show accuracy versus position gap or variance in performance as the position changes. For celebrity, we can see that gender bias and position gap both are high. For word dataset, as we go from in distribution sample, Qwen72B and intern VL14B look robust at the ideal zone, but the moment we go to out of distribution samples, all the performance is dropped. Similarly, having a closer look for the robustness for out of distribution sample versus in distribution sample for attribute localization task. A simple task like transferring all the attributes in support to query, we see that models like Quen, Gemma all fail. But as we go to the single attribute, like from average performance to a single attribute of mouth, we see this gender bias is much more wider. Finally, our findings on think tokens, we observe that models perform really good fixing the ambiguities on clean, unchanged images and actually fix much of the ambiguity in the early tokens. But even if they are spending time with 3000 token length, they still end up fixing more. Compared to when we introduce out of distribution sample, the fix versus fail ratio is increased. There are less fixes than more fails, suggesting that thinking doesn't really help in perception. Finally, on the closing note, we see that thinking is almost waste of compute for perceptual task. Models do explain better without actually perceiving what's given in the image. In future direction, we would like to explore perception first training, visual grounding with counterfactual and hard negative samples, along with confidence calibration whenever there is a out of distribution sample, models to use reliable tools to calibrate their uncertainty. Please try out Perceptual Observatory yourself. Both code and project are available on the QR code. Thank you.